so I think this would be a good test for us to see the format as well. So feel free to add, because I'm pretty sure that the four of us that are here today have a lot of stuff to add. And yeah, perhaps we can do the next session in Discord as well, because this way it's going to be easier for me to share your audios as well. So I think this will be a very interesting thing.
Sure, Ricardo.
Okay, let me just try something here, because I might be able to do it now, I think. Well, this will be a test. If it works, fine. Or if one of you guys can join the YouTube broadcast just to check if the audio is fine.
Yeah, can you share the link?
Okay, 1 second.
I'll just search you up on YouTube.
It's this.
Yes.
So can you guys hear yourselves? That's the thing. Because if you can, that's going to be perfect. Because this way we can all talk.
Yes. Let me just.
Yeah. And I'll probably edit this initial part and remove this technical issues introduction afterwards. It was really interesting to see how
So the YouTube is running a little late. So just
it's I added a 30-second delay.
Yes. So just 30 seconds and I will get to know if I'm speaking or not.
Yeah, I'm speaking.
I was able to hear Farhan's voice there.
Oh, that's perfect then. All right, so I'll just go ahead and get started then. It's hard to talk about quantum computing without committing two very big problems. The first one is going into the hype of only talking about the hard stuff. And there are a lot of videos out there that talk about quantum in a funny way, because it almost makes it sound as if it were something related to a sci-fi movie, and it is not. It's just technology, and any technological advance that humanity has reached over the times, when it's something new, it's impressive, it's sometimes scary, and it can be confusing. But it doesn't mean it's impossible to understand, which brings me to the second biggest mistake. I'm still doing that, actually. I've been reading a lot of introductory material to try to come up with the easiest way to convey the knowledge regarding quantum computing specifically to a general public. Of course, this is hard because we're talking about something related to quantum mechanics, which is a totally impossible field to understand, at least for me. It's super hard, but it's feasible, especially when we look back at the history of the quantum mechanics field itself, because people were studying it even when the whole Einstein issue wasn't solved because of mathematics. So this is the approach I have decided to take. This is a initial test. Actually, there are a couple more things that I would like to try in the future. One of them is using the trigonometry circle, but there are still some issues with that I'm working. Anyway, I'll just get done with the talking and start introducing the topic that I am going to talk about today. As it says on the screen, I hope this is visible. This is a brief introductory talk on quantum computing, and we are all members of the QPower community, and we are devoted to promote knowledge, to a broader public regarding quantum computing, and also to research new technology as well. Basic requirements for this video: you must at least be able to understand what matrices are and how to do matrix multiplication. So I am not going to be teaching you this, and I will be using Python as well, which in my opinion, even though it's kind of messy, it has some problems, but it's the most powerful language that we have access to because of its versatility. And also, since we are choosing for now to focus on Qiskit, which is a Python library that deals with quantum implementation, this is our choice. Anyway. So information, when we talk about quantum computing, it's important to understand what computing is. And we're talking about a major process that was in the 50s and the 60s, a process that mathematics started involving how to process and how to understand information. So computation and information are two very close theories and sciences. I think I can call them sciences. I am going to simplify it very much by saying that all we do in computing resumes to getting a certain input in information at an information format, processing it, and then coming with an output. So this will help us understand some of the differences between bits and qubits, which are the fundamental units of information in both classical and quantum environments. There's a link here. I'll be sharing the link to this Python notebook in the video as well. But I'll be running the cells, and please, Farhan, Rohit, and Raghav, feel free to talk whenever you feel you need to make any input. There's a very link.
Yeah, sure.
There's a very cool link here if you guys want to read on the first article that introduced the concept of byte and bits. So the bit is the fundamental unit of information within the classical computing environment. And I'm going to use the matrix representation, which is here. I would be glad to use the Dirac notation, but I don't know how to add that second symbol, the similar to the greater than on LaTeX, without adding the physics package. So we'll define here then the 0 and the 1. Okay, let me back up a little bit. So a bit, it's something that's able to store two positions, two states. It's easy to understand 0 and 1 because that's what we see in all those movies, especially in those Matrix movies, the green screen and whatever. So it's 0 and 1, on and off, there, not there, current and no current. So this is how it looks like in the vector notation. And it's just to check the bottom number, and then you'll be able to memorize it easier. So 1 and 0 here. And in classical computing there are 4 what? Oh, okay. Let me run this first cell because this is not gonna work if I don't do it. Okay, so there are 4 basic operations that we can do with bits. And just to define here real quick what an operation is, it's just something that when I said processing information, this is basically an operation. This is taking something as an input and then generating an output. And it's a function because we're in classical computing, it works as a math function. So I can only have one output here. So identity, so the output it's equal to the input, so f of x is equal to x. Negation, f of x will be the inverse of x. In case of 0, 1, 1, if I input 1, I'll get 0, and vice versa. Constant 0, no matter what I insert, the operation will get an output of 0, and constant 1, the same thing, but for the value 1. And just by using the identity matrix here, I can get the identity, which is the first operation. And if you know anything about matrices, I don't think I need to explain this much more than that. So as you can see here, if we take the identity and do the processing with 0, I will get 0 in output, and the same way for the 1 here. Negation, this is just to show programmatically the results of what we already discussed. So negative of 0 is 1, and negative of 1 is 0. Constant 0, as expected, everything will return 0, and constant 1, the same thing. So reversible operations, and as I said before, I will be simplifying some concepts just to understand, just to make it easy to understand certain ideas. And reversible computing is a very controversial topic. There's a significant discussion, ongoing discussion still. But I'll just say that I'll just define reversible operation as any process that allows the identification of the input just by knowing the operation used and the output. For example, if I know it's an identity and the output is 1, I know that the input is 1. And the same thing applies to 0. This means that identity is a reversible operation. Opposite of this, the constant 1, for example, if I know it's a constant 1 and the output it's obviously 1, I don't necessarily know which the input is, whether it's 0 or 1, because all the output it's the same. In other words, classical bits and their operations are not always reversible. They can be, but they're not. And just to explain the discussion that I was referring to, there are some theories of thought that postulate that even though these things happens with bits, they are still reversible. I'm not going into further details about how that is how exactly that is established. Tensor products, which is something that not all colleges cover in linear algebra, so I'll just explain briefly. There's also a link of a very cool course by NASA. Basically, if I have two matrices, x0 and x1, y0 and y1, their tensor product is as if I were multiplying x0 by this whole matrix and then x1 by this whole matrix, and this is what I get as an output. Another example here, for a triple multiplication, and I'm just showing this here because I might be talking, I'm not sure, I might be talking about an example of this kind of multiplication when I cover the quantum bits notations. So everything I've talked so far refers, the operations, for example, refers to one bit and how we visualize these. But we can represent multiple bits in the vector notation using tensor products. So for example, if I have 2 bits, I can have 4 possible states, 2 of them being 0 or 0, 1, 1, 0, and 1, 1. And the first state, which is 0, 0, 0, 1, the second state, 1, 0, the third state, and 1 1 the fourth state. And this is reversible, right? I can reverse this operation. From this I can obtain these two. For example, here I can easily see that this is the first state, so it's 0 0. I know this is a 0 and I know this is a 0, and the same thing applies. One problem of this notation regarding classical bits, and this is something that will help us see the power of quantum computing, is that this grows as exponentially. So if I have 10 states here, I would have 1 0 2 4 lines here, 2 to the power of 10, and this would be impossible to represent this way, right? But still, this is a very useful notation because it's easy to get I can reverse this and obtain the inputs quite easily. So the same example here, using NumPy to display. So the 0 0, it's the product, the Kronecker product, the tensor product of 0 0, 0 1, 1 0, 1 1, and as you can see the outputs here, the first state, the second state, the third state, and the fourth state. Let's talk about an operation which will be important, and just a note here.
Ricardo,
yeah, sorry, my cat.
sorry to interrupt.
Yeah, you're good. You can.
I wanted to add something
Sure.
which I find interesting regarding the exponential growth of the tensors. So when we talk, mostly we consider column vectors, the tensors, which tend to grow again into a column vector. But even in the case of matrices, so if we have 2 cross 2 matrices, when we take the tensor product, it grows into 4 cross 4 matrix, and when we take 2 4 cross 4, it grows into 16 cross 16. So that is something amazing, like how the growth is actually done with the matrices as well.
Yeah, and yeah, thank you for sharing that. I think this is a very powerful tool, actually, and not only that, but I like this notation as well, and we'll be discussing that for sure when I talk about the quantum, because it allows us to see the probabilities as well. Let's just advance for a second, but for example, if this was a qubit, I would know for sure the probability that it would collapse in one of each one of the 4 states here. So it's beautiful. It's just beautiful how mathematics is able to explain physical concepts in a rather coincidental way, right? Because these theories were developed completely separated from each other. So just something real quick. I am not going to cover all operations with multiple bits. There are more than just the C0 gate. Okay, so whenever I say gate, I mean operation here. Let's just establish that so people don't get confused as well. So the C0 operation is one of the fundamental building blocks of reversible computing, which is the conditional not, the control not. So it works in pairs of bits. So one will be called control and the other the target. So this gate will behave in the following manner. So if the control bit is 1, then the target will get flipped. Let's say if the target is 0, it will become 1, and vice versa. If the control bit is 0, then the target won't be changed. The control bit for this operation will never be changed. And the most significant bit in this representation here, the 0, 0, 0, 1, 1, 0, 0, 1, and as well as in the direct notation that we don't have here, is always the control, and the other one will be the target, just for these representation. And again, an example here using NumPy. So this is a C0 matrix, and again, for those who have any familiarity with the with linear algebra knows the power of this matrix. It's very similar to the identity matrix, but it reverses the two last columns. And let's see the power, the result of this. So let's apply the C0 in the 0, 0. And what happens is that the control bit is 0. So as expected, the target bit will remain unchanged. And remember, this number 1 here represents the first state, which is a tensor product of 0 and 0. So the result is still 0, 0. And the same thing for the 0, 1. So the 1 in the second row will represent 0, 1. So it remains unchanged. But they get flipped if we apply into 1, 0 and 1, 1. So 1, 0 becomes the fourth state, which is 1, 1. And 1, 1 becomes 1, 0, which is the third state. And interesting thing so far, we've been talking about quantum, about classical units, the bits. But everything we did here, it's exactly the same thing for qubits. We can consider all these matrices as particular cases of qubits, and we're going to use the same vectorial notation to discuss the properties of qubits. So I've written down something here that it's not entirely true, okay? But let's just consider it is for now. So all operations within quantum bits have to be reversible. And we'll see in a minute why am I saying that this is not exactly all true. Because in quantum mechanics they are always reversible, okay? But for some mathematical reasons we'll see that we'll use representations that are not necessarily reversible. So let's just define a qubit as a vector AB in which both A, B are complex numbers, and the moduli of A and B squared added together needs to be equalized to 1. So it's just a normalized notation. And again, we'll see in a minute why we need these values to be normalized as well. So for example, -1, 0, and you see here we can have different values than 0 and 1. Half, square root of 3 divided by 2, and all these, if you calculate the absolute values squared here, you get the 1 as a result. So, and then I'll go back to the sci-fi for a little bit and talk. So this is a mathematical explanation of how qubits can be 1 and 0 at the same time. And we'll resort to probability to explain this. So let's say, for example, here, this is going to be a simplification, but let's say that this qubit, the 1 divided by 2, the square root of 3 divided by 2, it will have these probabilities, A squared and B squared, of collapsing into each of the states 0 and 1. I have an unnecessary extra cell here that I'm going to delete. Okay, so let's go back to the reality. As I said before, the probability of a qubit AB to collapse to 0 is the moduli of A and B squared to 0 and 1. So this will help us to understand the behavior of a multiple qubit system. As I said before, this representation explains qubits just as well as it does bits. So let's take this example here, the third example. 1 divided by square root of 2, 1 divided by square root of 2. And let's calculate a 2-qubit state. So I apply the tensor product here with these 2 qubits, and the result is half, 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 half. 0.5, 0.5, 0.5, 0.5. which means for this that it has a 1 divided by 4, 0.25 probability of collapsing in each of the 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. And since we're dealing with probability, this explains why we need to normalize these vectors, because the sum of a probability needs to result always in 1. Okay, so let's go ahead for some quantum gates. So the first one is the Hadamard Gate, which will take a qubit in 0 or 1 state, and it will put it into exactly equal superposition. What is superposition? Okay, just going back a little bit, I briefly spoke about the whole idea of a qubit being able to be 0 and 1 at the same time. So the only way I have currently, not just me, everyone, of knowing the value or the state of a qubit is when we measure it. And I'm not sure if you guys remember from the physics class the whole idea of looking into quantum stuff, and when you look at it, it behaves differently. So it loses this superposition, this confusing property, and it becomes either 0 or 1. But when no one is looking at it, that's when it behaves weirdly. So let's just say that the Hadamard will take a qubit in a regular state and put it into the confusing state. And what it means here, exactly equal superposition, is that it will be put in a position in which it has the same probability of collapsing either to 0 or 1. So this is its matrix. So it's square root of 2 divided by 1, 1, and multiplied by, divided actually. 1, 1, 1, and minus 1. So if we apply it to the qubit 0 and the qubit 1, we'll have this, which is 1 divided by square root of 2, 1 divided by a square root of 2, which is the same, this matrix up here. This vector up here, yeah. So, and what happens, this is the interesting question, and I'm well aware that you guys know the answer, but let's just have a quick discussion here. So what happens if I apply the Hadamard gate to one of these qubit vectors in superposition? Yeah, if any of you guys, if you want to talk about it as well. Farhan, Rohit, or Raghav.
Raghav, would you like to take that?
Yeah, Ricardo, I didn't quite get which vector you are applying.
Oh,
the Hadamard Gate.
the outcome here. One square root of 2, 1 square root of 2.
Okay.
So yeah.
Okay.
Yeah.
I think you can continue. I can't. I don't have a confident answer.
No. It's just the idea. I'm taking it 0 or 1.
Wait, are you asking what's the superposition gonna be after you applied the Hadamard gate to 0 and 1, or is it like Hadamard gate to the already applied
to the already applied superposition vector?
Mm-hmm. All right. Double H. Yeah, you head back whatever you had.
Exactly.
Yeah. Yes.
So this is interesting. And this doesn't happen, as I said before, it doesn't happen in all gates in the classical computing. So it means that Hadamard is its own reverse. So if I take it,
Ricardo, actually, we are having some delay in the YouTube session, which has been going live. So we are not able to see the screen in Google Meet. So yeah.
Probably you can also share your screen here.
Yeah.
Google Meets.
We're just seeing the Meet window here.
Can you guys see the screen? I don't understand what's going on.
Yeah, now we can see.
No, we are not able to see your notebook on Google Meets.
Yeah, it was all the time. It was just the Google Meet
YouTube
screen
session.
itself. Yeah, now we have this thing, the YouTube Studio.
Oh.
I think you have to share the window. You're scrolling the Jupyter notebook, so that it would be synchronized.
Yeah, I guess you'll have to stop sharing here and then reshare the window where you're actually using the Jupyter notebook.
Yeah.
So I'm confused. In here was
sharing? Here you will have to. Yeah, here you will have to stop the share and then reshare the window you are scrolling for the YouTube stream. I think that would do it.
Does it work now?
It's loading.
Yeah.
Yeah. Now it works.
Oh, perfect.
Yes.
Perfect.
Oh, yeah. That explains everything. So I'm sorry for that. Yeah, it's still an ongoing test.
Yes.
Okay. So yeah, back where I was. So the Hadamard Gate is its own reverse, and this is true for almost all gates in the quantum environment. So let me show another notation that we'll use to deal with the gates, which is a circuit notation. All these are going to be very, very simple here, because this is just an introductory thing. So I even created a challenge here. Let's see if it's going to load properly. I hope it does. Yeah, so if I take a qubit in the 0 state and apply the X and then the Hadamard, this is why, remember I was talking before about using the trigonometry circle, and I think this is going to be awesome for these kinds of things. For example, I'm not going to take this as a challenge. I think I'll just show, I have an idea, 1 second. Yeah, I think this will be a good idea. Let me just grab a unit circle here and let's use it as a reference for this. So we'll take something with good quality. This will be perfect. All right. Whoa. All right. So yeah. So let's do this challenge together. And this is why this notation will be helpful. So if I take a qubit in the 0 state and apply the X gate, I'll explain the X gate later. So what this circuit means is that these operations will be taken sequentially. So I'll apply the X gate first, and then the H gate, and then the X, and then the H, and then the X. And let's imagine here that I have a measurement, and then I'll know the outcome. So if I take the X gate, which means I'll flip it. If it's 0, it will become 1, and that's what I do. And then I apply the X gate, and the qubit will be here at the 1 state. And then I apply the Hadamard gate. So where will it land? If I apply the Hadamard gate,
it's gonna go to the negative X direction if you're applying it on
right here,
the
right?
1 state. Yes.
Yeah.
Yes.
So it will go here. From here to here, it will go from pi divided by 2 radians to 7 pi divided by 4 radians. And then if I apply the X gate, it will flip into here. So remember, I'll just reverse these two. So I have negative and positive here. It will flip pi radians. And then if I apply the Hadamard gate again, where will it land? It will land here, 3 to the opposite side. And then if I apply the X gate, it will end here at -1, 0. So just I'll work on that later, but each one of these gates can be represented here as well in the trigonometry circle. I'll just delete this for now because I'll make it smaller. But since I started talking about the polygates, and the polymatrices are widely known in linear algebra, especially in the complex linear algebra, but let's skip the math and just explain what they do. So, and here I'll resort to a cool thing that Qiskit has, which is the block multivector. And I haven't used the block notation here purposely. I think we can cover that later and introduce some interesting concepts as well that I think will be very useful. But what the X gate does, as we said before, it flips a qubit pi radians around the x-axis of the sphere. So if I start a single qubit initialized in the 0 state and apply it, the X gate, I flip it to 1 and it goes down here. And if it was we were applying it to 1, it would flip it to 0 as well. So the poly Y and the poly Z work similarly, spinning it to the pi radians around the y-axis and pi radians around the z-axis here as well. So and from now on, I'll be talking about some particular gates that aren't reversible, and perhaps we can even dive in deeper into that later. But the R or the RZ gate is a parameterized gate, which means it requires an additional parameter to work, which is this number of degrees here, and it will perform a rotation along the z-axis. So our phi 100 e power I times phi. And another gate that we have, I'll just mention it, it's the identity gate. The I gate does exactly what we expect. It doesn't do anything, but there are some applications to it, but we won't be discussing them here today. The T gate, which is just an R phi with the phi equals pi divided by 4. This is very, we use it a lot actually. The S gate, which is another particular case of the R phi with phi being pi divided by 2. So if we apply it twice, we would get a Z gate. So in the T and in the S gates, I have the T dagger here, which would be an equivalent to the other side. And it's my fault here. I forgot to add the block sphere notations to make it easier to visualize. But as you can see here, down here in the parameter, you'll see the difference between these two. But what matters is that they all spin the qubit with the same number of degrees here. Pi divided by 4 in the case of the T, and the S pi divided by 2. All in the Z-axis. And all these gates are particular special cases of the U3 gate. Due to its complexities, we don't use it a lot because it's basically explaining like a general rotation of a qubit within any angle within the block sphere. So this is its definition. And what Qiskit does is internally, when we write any circuit like this, like the one we have here, it will compile and transform all operations into U operations, either U1, U2, or U3. And the U1 is the R phi, and U2 is just with theta equals pi divided by 2. So there are an infinite number of possible operations, and these just briefly cover some of the basic stuff we can do with a qubit. And so if you guys have anything else to add, I didn't put all the gates here, and as seen, since Qiskit itself doesn't have implementations for x and y equivalents to the s and t, for example, which are rotations in the z axis, and these are two things that can be implemented in the language in the future as well. But anyways, it was just a matter of a choice, a more practical choice, just to stick with the z-axis for now. But do you guys have anything to add here?
Oh no, I'm good. Just that we have U2 and U1 gates as well.
Yeah. Yeah, on Qiskit, yeah.
Yep.
But it doesn't allow the U3, right? Not in an upper level. At least I didn't find it.
No, I think U3 is also there. You can apply, and it has theta, phi, and lambda as the parameters. You can apply that.
Oh yeah, no.
It's just the quantum circuit dot U3, and then you
Yes.
Oh, so
Even their controlled counterparts they have as CU3, CU2. They have that.
Awesome.
Yes.
So let me fix this then, because I didn't find it. Okay. There are two special cases. Coding live.
Awesome.
All right. So yeah, let me then I'll stop sharing, and then I'll hand it over to you if you want to take over, Fran.
Yeah, I think Raghav, would you like to? Would you like to just discuss the textbook chapter that you've read?
Yeah, sure. Like honestly, I feel Ricardo has covered most of the basics, like almost everything. But I would yeah, I would be happy to cover it up. Yes.
Yep, sure. I was
Yeah.
supposed to give a Q sharp lesson as well, but anyway, we are focusing on Qiskit, so
Yeah.
let's leave it for some other time.
Actually, I wanted to share one playlist related to linear algebra.
Oh,
Since
Sure.
we are discussing about quantum mechanics, and we know it is actually helps when we can visualize how matrices, transforms vector. So I found this playlist, a sense of
Is
linear
it is
algebra.
it is it the Khan playlist? I don't
No,
remember the.
it's by Three Blue
Three
One
blue,
Brown.
one brown.
yeah.
Oh,
Yes.
okay.
Yeah.
Okay.
So probably if our viewers go through this, they'll be able to understand it better.
Okay. Even I had come across one playlist. It's Academy of Khan. The name of the
The
playlist.
Khan
The name
Yeah,
of
the
the
Khan Academy,
channel actually.
Oh.
Yeah, and
Yeah, I don't know that one. I
yeah,
have to check it.
yeah. It's the name is Academy of Khan.
Okay. So will you be sharing your screen, Raghav?
Yeah, I
Okay.
can share the
Alright.
screen. And have you stopped the YouTube broadcast? Uh, because how are we gonna connect my screen to it?
I
I
can
think
do that. Don't worry.
Okay, you can do that.
Yeah. As long as you share it, I'm good.
Okay, sure. But I don't have honestly a lot remaining
Don't
from
worry.
this textbook chapter as well.
Don't worry. Don't
I'll
worry.
try to. Yes. Just a second. Can someone tell if it's my screen is visible?
Yeah, it's visible.
Yeah. Okay. So yeah, I also you were going through the visualization part. I had this really nice tool. I thought I can just put up the same example on this visualizer.
Oh,
So it would
that's
be
going to be perfect. Yeah, that's
yeah.
perfect.
This is actually very nice. So yeah. I think we can go on with all the demonstration of all the gates. I think that would be
Yeah,
good.
yeah,
So yeah, this is the general block sphere which we talk about. Uh, it comes from the Hilbert spaces concept from mathematics, but it is a very a very efficient way to represent a single qubit. Basically, the space of all states that a single qubit can take up is very well represented from a block sphere. So, and it's something to be noted. It's only for a single qubit. We can't represent two or more than that qubits on a single block sphere. It would be really complex. So we have this zero. Is my cursor visible?
yeah.
Yeah. So we have the zero ket on the top, and we have one ket vertically at the bottom, and this is what we have in the block sphere. But when we talk about 0 and 1 ket, we say they are orthogonal in nature. So what we mean by that is like any given state, if it's known to be residing in the 0 ket, cannot be present. Like it cannot be having any probability of being in the 1 ket. So that's the main definition behind two directions or two vectors being orthogonal in nature. So orthogonal, we often tend to have the conception of two vectors being in a 90-degree angle, but that's not the case in a block sphere. So that's something to be noted. Then we have the x basis, which is the plus minus basis. Again, the plus state is the 0 ket plus 1 ket, which is what you get on the application of Hadamard Gate. So I think I'll just try it out. So right now we have our state at the 0 vector. When we are applying this Hadamard Gate H, we see the vector goes into the plus state. So the plus state, yeah. So we have the general equation termed here. So for if we take the representation, the state as phi, we have 0 state in the probability of 1 by root 2, and the 1 state in the probability 1 by root 2. So that's what signifies the superposition with equal with the qubit basically collapsing with equal probability in both 0 and 1. And when we are on the 1 state and we apply the Hadamard gate, we'll come to the minus state, which is again yeah. So all the two vectors which are residing in a basis, both of them are orthogonal to each other. So again, just like 0 and 1 are orthogonal pair, plus and minus state are an orthogonal pair. And the one state, the minus state is going to be 1 by root 2, and you see a pi term, a pi constant reflecting here. So this, when we like simplify this, we're gonna get a negative sign here. If we represent it as cos theta plus iota sine theta, we'll be getting a negative sign here. So essentially, it's again signifying, if we talk about the amplitudes of 0 and 1, they're again 50% each, but the negative phase is what tells us if we are in the positive side or in the negative side. And coming back to the 0 state, when we apply a NOT gate, that is basically the poly X gate, where we'll be going from 0 to 1 and coming to the positive state, and then if we apply an X gate, yeah, so this is going to be okay. So anyone can make out why we are staying in the positive state on applying the X gate? Any guesses? Farhan, Ricardo, anyone?
Yeah, Rohit and Farhan, I spoke too much.
Okay, I'll
Yeah,
continue. Acha, yes.
so we are getting a positive state, you can say, because we are going anti-clockwise direction.
Yeah, or we can simply represent it. We can, address it as so. The poly X gate. What does it do? It reverses the all the states which are possible to be achieved on measurement.
Right.
So the positive state signifies 0 ket plus 1 ket. If we apply
Right.
a poly X gate, we are just getting 1 ket plus 0 ket, which is again the same state. So that's why we are staying in the positive direction. And when we go to the negative state, it's going to be the same. Yep. So that was the poly X gate. And same is the case for Y gate. It's just that the X and Y and Z, they represent in which about which axis we are doing the rotation, the 180-degree rotation. So if I apply the poly Z gate in the Z basis, so we take the plus and minus basis as X, the iota and minus iota basis as Y, and the 0 and 1 basis as the Z. So if I apply poly Z, there wouldn't be any effect, because the poly Z gate rotates about the Z axis, which would not be a significant change. So yes, you can see that even on the positive state. So when you see the phase representation, only the phase is changing. So we will be getting a negative sign here. But again, the basis and even the state in which we are remains the same. So when we collapse it before applying the poly Z and after applying, we'll be getting the plus state, the one state itself. And yeah, I think the visualization is done for now. Yes, the RX, RY, and RZ gates are again rotations about X, Y, and Z respectively, given your own parameter theta. So you have two options in this simulator. You can apply anything when you're coding it out in Qiskit or C sharp, Q sharp. So yep, I think so. This is the Qiskit textbook. It is pretty well documented, starting from the basics, and yeah, I think Ricardo has covered a lot of it. I think measurement part is left. Yeah, so I think I
Yeah,
can talk a little bit about it.
yeah, we can either do this or I don't know. We can take measurement and talk about it with entanglement as well, because which is something that I didn't cover. I
Okay,
don't know what you guys
right.
think. Yeah, I don't know what you guys think.
Uh,
If we can also
okay.
use other circuit identities or as
Yes.
well.
I think that would be good. Also, yes. I
Yeah,
think.
sure. We can do that.
Yeah. Right. So are we done?
All right.
Yeah, I had a question actually. Can you try the
Oh.
S-stagger gate actually?
Yeah. Just a second. Sorry, I stopped my
Yeah,
screen.
no problem.
Hope you can see my screen.
Yeah.
Yeah, it's
Yeah.
coming. Yeah, there it is.
Yes. So we're on the zero state. So S dagger state would be the complex conjugate of S gate, and I think yes, it doesn't have any effect on the zero state. Yes, but if we
Yeah.
jump to the plus
Apply
state,
the Hadamard and then apply it.
yes. Yep. So we get a 90-degree shift to the y basis, and the S dagger would give a negative result, I guess.
Yeah, it will spin it in the opposite direction.
Yep. Yeah, we're going to the negative y basis. Yeah.
I really like this this website because if you see it has both the block sphere and you can see the projection down below with the radians.
With the
this is
phase,
very
yes,
useful.
yes.
This is a very useful tool.
Right.
If I had it, I would have surely be using this. Or do you think this can be embedded in a notebook? I don't know the code.
I'm not the person to
Yeah.
try out that. I guess
I'll
you
check-
can
I'll
try
check
that out.
I think it's a GitHub page, so if you can go to the
because if
Java
I see it,
or
it's,
GitHub.io,
it's
you might
probably
be able
a
to get some.
Java thing, but yeah, I think we can transpose this to Python. Yeah, let's try doing that this week.
Yeah, that would be awesome actually.
Yeah.
I just shared the link with you on WhatsApp. Like I did it on the.
Yeah, that's a great tool. So yeah.
Yep.
Anyway, unless you guys have anything else to add, I'll just wrap up here.
I think we're good to go. We can end the stream.
Yeah, I'll just share something real quick for a second here. Can I do this differently? Yeah, I'm trying to share, but I'm using the PowerPoint live thing because I'm on Linux, and I think I just lost what I did. Oh yeah, I just lost what I did. Anyway, so I'll be adding to this link as well our links to the QPower Research page, and soon we'll have a GitHub repository with all this content. So yeah, feel free to reach out. So this broadcast was done from my channel because we haven't configured our channel. We also have a channel as well, and feel free to follow it. I'll be adding all these links into this video. So yeah, thank you guys for your help, and yeah, I'm looking forward for next week's for our discussion as well.
Yeah, thank you, Ricardo.
Good evening, you guys.
It was an amazing session.
Thanks, guys. Thanks, Ricardo. Thanks, Raghav, for the sessions.
Thank you, Rohit.
Thanks, Rohit. Yeah.
Yeah, thanks.
Yeah, I've just
Thanks,
finished the